Hello, everyone. In this lecture, we're going to look at the concept of continuity or continuous functions. The learning objectives for the lecture is to explain the three conditions for continuity at a point and describe the three different kinds of discontinuous or three different kinds of discontinuity. And also, we learn how to define the continuity on an interval. Often, the limit of a function as x approaches a can be found by calculating the value of function at a. Function with this property are called the continuous functions. So in the previous lecture, we can find the limit of a functions by direct substitutions because the functions that are chosen has the property called the continuous function. So for definitions of function f is continuous at a number a, if the limit of the function f of x as x approaches a is equal to f of a. There are three things are required if f is continuous at a. The first thing is that f of a is defined. So that means that a is in the domain of f. The second point is that the limit of the function has to exist. So the limit of the functions as x approaches a exist. And from the last lecture, we learned that the limit exists when the left-hand limit equal to the right-hand limit and equal to the same value. And the third requirement for a functions to be a continuous function is that the limit in step 2 has to be equal to the evaluations of the functions at that point A. Okay, so for instance, given the graph right here, we know that the function exists at x equal to a because you have a closed circle right here. At the same time, the limit of the function as x approaches a from the left equal to the limit of the function as x approaches a from the right. Therefore, the limit of the functions approach to the same value. And by looking at this graph, you can see that the limit of the function is equal to the evaluations of the function at x equal to a. Therefore, this function of considerations right here is a continuous function. Now let's take a look at an example for this given graph. We can identify the point at which the function is not continuous. Okay, so there's a few points in this case. So at x equal to 1, in addition to that, the function is not continuous at x equal to 3. Even though the function is defined at x equal to 3, the limit does not exist because the left-hand limit does not equal to the right-hand limit, and therefore the limit does not exist. It failed one of the requirements that we have earlier. And the function is discontinuous at x equal to 5 because even though the limit exists, even though f of 5 is defined, the value of the limit and the value of f of 5 are not equal to one another. So therefore, the function is not continuous at this point. So we can write that the functions is discontinuous at x equal to 1, at x equal to 3, and x equal to 5. We can clarify the idea of discontinuity as follows. So at x equal to 1, you can see that f of 1 is not defined. As x equal to 3, the limit does not exist. So the limit of the function as x approaches 3 does not exist. And at x equal to 5, the limit of the functions as x approaches 5 does not equal to f of 5. Because of these explanations, we can draw the conclusions that the function is not continuous at x equal to 1, not continuous at x equal to 3, and it's not continuous at x equal to 5. There's another way to ask the questions. That is, can you list the interval on which the function is continuous? So by looking at the graph, we can identify those intervals. So from here, I can identify that the functions is continuous on the following interval from negative infinity to 1, comma from 1 to 3, and from 3 to 5, and from 5 to positive infinity. And remember, we don't use the close brackets to indicate the interval of continuity. Now let's move on to different type of discontinuity. There are 3 types of discontinuity. The first one is called removal discontinuity. So you can recognize this type of discontinuity when you look at the graph and you identify there are some holes, and at the same time, the limit has to exist. The second type is called infinite discontinuity. And the last type is called germ discontinuity. For the germ discontinuity, you can recognize this type of discontinuity when you have some holes. And also at the same time, the limit does not exist at that point. So for instance, given 4 different graphs, the first graph right here is discontinuous at x equal to 5, and the type of discontinuity is removable discontinuity because there is a hole here, but the limit exists at that point. So this is called the removable discontinuity. In the second graph, the function is discontinuous at x equal to 0 because as x approaches 0 from the left, the functions go up to positive infinity. Or you can give the same explanations, is that when x approaches 0 from the right, the function approach positive infinity as well. So for this graph, the type of discontinuity is infinite discontinuity. In the third graph, the type of discontinuity is the germ discontinuity because you can see here there are holes, but at the same time, the limit at the point of consideration does not exist. For example, the function is not continuous at x equal to 0, and the discontinuity is germ because the left-hand limit does not equal to the right-hand limit. So I conclude this is the germ discontinuity. Now for the last graph, the function is discontinuous at x equal to 2. It's called the removable discontinuity because there's a hole here and the limit exists at that particular point of considerations. So this is removable discontinuity. So again, there are 3 different types of discontinuities. The first one is removable discontinuity. You can recognize this when you look at the graph and identify there's holes and the limit at the point of considerations exist. The second type is the infinite discontinuity. When you consider the limit at the point of discontinuity, the limits go up to either positive infinity or negative infinity. And the last type is the germ discontinuity. Again, when you look at the graph, you can identify there are holes, but the limit at the point of considerations does not exist. Now let's move on to a couple of theorems. So for the first theorem, if f and g are continuous functions at a and c is a constant, then the following functions are also continuous at a. So the first functions is c times f, right? So if f is continuous, the constant multiple function is also continuous at a. The combined functions f plus g is also continuous at a if f and g are continuous at a. The combined functions f minus g is also continuous. The combined functions f times g is continuous. And the quotient functions f over g, given that g is different from 0, is also continuous at a if f and g are continuous at a. In the second theorem, it say that the functions are continuous on their respective domain. So the first functions that we want to consider is polynomial functions. The second functions is rational functions. The third function is exponential functions. The fourth function is the logarithmic functions. The next one is trigonometric functions. Number 6 is inverse trigonometric functions. And the last one can be absolute value functions. So remember, all of these functions can be continuous on their respective domain. So that means anytime you have this type of function, the first thing you need to look at is to find the domain of the functions. Then you can draw the conclusions on the continuity of the functions. Now let's take a look at the following example. In this example, they ask that for what values of x is f of x equal to x plus 1 over x minus 5 continuous. So this is the rational functions. And the first thing you need to do when you see a rational function is to find the domain of the functions. And remember, for rational functions, the denominator cannot be equal to 0. So x minus 5 cannot be equal to 0, which implies that x has to be different from 5. Therefore, the domain of the function is x different from 5, or the domain of the function is from negative infinity to 5, union with 5 to positive infinity. Right. So this allows us to identify the interval of continuity. Right. So the function is continuous on 2 intervals, from negative infinity to 5 and from 5 to positive infinity. So the functions is continuous on the interval from negative infinity to 5 and from 5 to positive infinity. Similar idea for the next example. In the next example, the function is also a rational function, and therefore the denominator cannot be equal to 0. Right. So we have to identify the domain of the function first, and then from there, you can identify the interval on which the function is continuous. So for this, the denominator x squared plus 2x cannot be equal to 0. You can see x is the common factor on the left-hand side. So this implies that x times x plus 2 has to be different from 0, or x different from 0 and x different from -2. So the function is defined on the entire real line except two values, -2 and 0. Therefore, you can write the domain of the function as x different from -2, x different from 0. Or in terms of the interval notations, you can write the function is defined on the interval from -infinity to -2, union with -2 to 0, and union with 0 to +infinity. And from here, you can draw the conclusions that the functions is continuous on the following intervals from -infinity to -2, from -2 to 0, and from 0 to +infinity. Let's consider example 4. For this example, you have a root of functions, or rather an even root functions, right? In pre-calculus, we learned that when you have an even root, the expressions under the root has to be greater than or equal to 0. So that is the domain of the functions. So in this case, x plus 3 has to be greater than or equal to 0, which implies that x is greater than or equal to -3. Right? So the domain of the function is x greater than or equal to -3, or you can write to +infinity. Therefore, the functions is continuous on the interval from -3 to +infinity. We have some other definitions related to continuity of the functions. So the first definition is that a function f is continuous from the right at a number a if the limit of the functions as x approaches a from the right is equal to f of a. And the functions f is continuous from the left at a if the limit of the functions as x approaches a from the left is equal to f of a. Now we're going to explore these definitions using the following two examples. So in example 5, given the graph of f, state the numbers at which f is discontinuous and classify the type of discontinuity. In addition, determine whether the function is continuous from the right or from the left or neither. So by looking at the graph, I can identify the point at which the function is discontinuous. So the function is discontinuous at x equal to -4, at x equal to -2, at x equal to 2, and at x equal to 4. So there are 4 points on the graph at which the function is discontinuous. Okay, now you classify the type of discontinuity. Remember, there are 3 different types of discontinuity: the removable discontinuity, infinite discontinuity, and the last one is the germ discontinuity. At the point x equal to -4, this is removable discontinuity because there's a hole, but the limit at that point exists. This is removable discontinuity. At x equal to -2, this is germ discontinuity because there is a hole, but the limit at x equal to -2 does not exist. So this is at x equal to -2, that is the germ discontinuity. At x equal to 2 is also a germ discontinuity. And x equal to 4, you have infinite discontinuity because as the limit of the function as x approaches 4 from the left, it goes to -infinity. Now, next, we need to identify if the function is continuous from the left or from the right or neither at this point. So at x equal to -4, the function is neither continuous from the right or from the left because the function is not defined at x equal to -4. So I conclude that this is neither. Now at x equal to -2, the function is continuous from the left because the limit from the left is equal to f of -2. Right. So this one is left continuous. At x equal to 2, the function is right continuous because the right-hand limit equal to f of 2. So this is right continuous. And at x equal to 4 is also the right continuous. With this idea, we're going to move on to another example. For this example, we have to be a little bit careful because the endpoint is not at infinity anymore. So the endpoint stop at -4 and stop at 8 on the right-hand side. When you have this endpoint, you don't consider the discontinuity at the endpoint at all. So do not consider continuity at the endpoint. So the endpoints are there for the domain of the functions. Okay. Now, by looking at the graph, you can identify that the function is discontinuous at the following points. So the function is discontinuous at x equal to -2, x equal to 2, x equal to 4, and x equal to 6. Now we need to classify the type of discontinuity of the point. At x equal to -2, it is the germ discontinuity because there are holes and the limit at that point does not exist. Now at x equal to 2 is also a germ discontinuity. At x equal to 4 is the infinite discontinuity. And at x equal to 6 is also a germ discontinuity. Next, we need to clarify if the function is continuous from the right, continuous from the left, or neither. So at x equal to -2 is neither continuous from the right nor from the left. At x equal to 2 is continuous from the right. So this is the right continuous. At x equal to 4 is neither. And at x equal to 6 is neither. So I hope this exercise help you understand the concept of finding the point at which the function is discontinuous, help you understand how to classify the discontinuities, and help you understand how to identify if the function is continuous from the right or continuous from the left or neither. So this is the end of the lecture. Please let me know if you have any questions.